All right, everyone. So in this lab, we're going to be considering conservation of energy. Remember, energy as a quantity is something that we can calculate about our system that can be based on motion. So there's energy of motion, and there's also energy based on height and energy based on shape. So we can say that there's also energy of height and energy based on shape. So energy of shape, among other things. So in a way, right now we can think of, like, let's say, the type of energies that we can have for our object, for a system, is at least, combination of those three types. Energy of motion, which means that if you have an object, for example, a box, if this box is at rest, then it doesn't have this energy of motion, because energy of motion assumes that your object has some kind of speed and is moving, and the energy of motion is given as Ke. So this is known as the kinetic energy. So let's call this, so basically it's a kinetic energy. Right, so kinetic energy then is given with, that's written as Ke. This is equals to 1/2 times object mass times its speed square. For example, if you have object that has a mass of 2 kilograms and moving at the speed of, let's say, 2 meters per second, then kinetic energy will be 1/2 times 2 kilograms times 2 meter per second square. So then this kinetic energy will be then 4 joules, because, twos cancel out and then you have 2 square. That means you have an energy of 4 joules. 4 joules basically means that you have certain object moving at some speed, and if kinetic energy is non-zero, that means your object is in motion. Kinetic energy is 0 always means that your object at that particular position, right, instant of time, has no speed and at least instantaneously at rest. All right, so now generally you can see, right, going from no kinetic energy to some kinetic energy, that's an information about object not moving and then moving. So generally, the more important quantity that we can actually use is changing kinetic energy. Because, for example, see if your object here has initial kinetic energy of 0 and then final kinetic energy of 4 joules, that means object basically went from one position to another position and changed the speed. So before it was not moving, now it's moving. Then you can say that changing kinetic energy is equals to final kinetic energy minus initial kinetic energy. And then that can tell you, in a way, if your object has any type of motion or not. So for example, now if this is 4 joules minus 0, now we get 4 joules, meaning that I have a positive change in kinetic energy. That means my object started moving faster. So that's an information that we can get from this energy. Now, energy of motion is relatively straightforward. It's just basically, that's the equation, 1/2 times mass times speed square. And it's 0 when object not moving. And then you can calculate kinetic energy when object is moving. The idea here is that there's also another energy, which is known as energy of height. And that's basically if the object has some kind of height relative to the, let's say, some reference. And the reference, usually the ground. So the ground, we can say that it has a vertical position of 0. So that's a reference. And if your object has any type of height relative to the ground, then your object has what we call energy of height. So energy of height is known as potential energy, written as PE. And you can see that potential energy is equal, or we can define that as the mass of the objects times gravitational acceleration, then times height. So that means this is then the equation for the potential energy. Now, that means you have a potential energy always if there's some height relative to the ground. And doesn't even matter if the object just hanging there, or it's on top of an incline like this, or maybe on top of an incline like that, or maybe on something like that, doesn't matter. As long as there's a change in height relative to the ground, your object has a potential energy. Generally, potential energy, remember, known as a stored energy, So stored energy, meaning that once you have potential energy, you can then convert this energy into different type of energies. One of the things about energy is that you can convert energy from one type to another, meaning that you can go from energy like a potential energy, convert to the different type of energy like kinetic energy. That means you can change your energy associated with height to energy associated with motion. Because, for example, if you're holding this object some height above the ground, then you let go, it's then going to start going down, where its height is going to decrease, meaning the potential energy is going to decrease, but it's going to start moving faster, meaning the kinetic energy is going to increase. Now, conservation of energy means energy in the system can never be created or destroyed. That means that's one of the important things about energy. So energy is a quantity that cannot be created or destroyed. Meaning, if you compare the energies between 2 points, if the conditions are correct, then your energy of, energy basically will just either be transferred from one system to another or be converted from one type to another. Now, the specific type of system and specific type of, let's say, configuration we're going to be looking at is configuration where the energy will be conserved. So it's a conservation of energy. And then it's going to be, the motion is going to be influenced by pretty much gravity. So that means motion under gravity. All right, so one of the things we have here is when the motion is under gravity, gravity basically conserves the total energy of the system. For example, if you have an incline like this, let's say you have an incline like that, okay, where you have 2 points. For example, here's point 1 and here's point 2. Okay. So when your object is here at point 1, and let's say it is moving with some velocity v, that means it has some initial velocity or initial speed at point 1. As the object starts moving to the left, because of the surface is basically curving upward, right? It's going to start slowing down. From the experience we know, right? If you're going a slope up the slope, you're going to start slowing down because gravity is going to start, pulling it, or slowing it down. That means by the time this object reaches this position 2, let's say this position 2 is specifically designed to be the highest it can reach until it stops. Now, one thing we have here is that this entire time, only force acting, so only force, let's say, affecting the motion is gravity. That means we have to eliminate any type of other forces. For example, no friction. We're going to say there is no friction. If there is no friction, that means object going from point 1 to point 2 will only be influenced by gravity. Remember, gravity always acting this downward direction. That means here it's acting down, here's acting down. But when it's going along the horizontal axis, gravity doesn't really affect its motion. But when in changing height, going from point 1 to point 2, gravity then is affecting. And because gravity acting in the opposite direction of motion, it will slow it down until it stops. Now, the idea here is then conservation of energy is possible when a force only acting is gravity, because gravity is a very specific type of force. So gravitational force, let me put like F of G, is what we call conservative force, which means it conserves energy. Now, what do I mean by conserves energy? Well, if I look at energy at position 1, I can say that here I might have 2 types of energies. Then we're going to be considering 2 types of energies. It's a kinetic energy and potential energy. And this is going to be specific for that point 1. That means energy at point 1 is specifically kinetic and potential, or the sum of those. At point 2, I can say also my energy that I'm going to be look at, where E itself is the total energy. So think like this: E is the total energy of the system, which takes into account 2 types of energy that we can, consider, which is energy of motion and energy of height, kinetic and potential energies. So their sum is, is the total energy of the system. That means when the, box is at position 1, the total energy is the sum of its kinetic, that means energy of its motion, and then potential of its height. Same thing for point 2. So then kinetic energy at point 2 plus potential energy at point 2. Now, conservative force like gravity, what it does, it conserves energy of the system. That means what I can say here is that energy at point 1 will always be equal to energy at point 2. That means sum of kinetic energy at point 1 and potential energy at point 1, not individual, but their sum will be exactly equal to the sum of kinetic energy at point 2 plus potential energy at point 2. All right, so that means this is what we call conservation of energy. And you can be a little more specific and call this conservation of mechanical energy, because when we're talking about sum of kinetic and potential energies, this is known as a mechanical energy. Okay, but we can just simply call this energy right now. The idea here is, since this is true, then we can explore and verify this. That means our goal in this lab is to verify if this is indeed true. That means we can calculate the energy of an object at point 1. All right, sorry, it's right here, energy of the object at point 1, and compare it to the energy of the object at point 2. And hopefully they will be exactly the same. The idea here is, if I'm simplifying my equation, see, on the left side, I have kinetic energy at point 1 plus potential energy at point 1. See, when the black starts from point 1, then goes up a slope to the left, at point 1, it's on the ground. And potential energy on the ground is always 0. That means I can come back and say that this is 0. But when the box reaches point 2, which is its highest point, remember, that's the highest point, it's going to move up until it stops. Well, there is no kinetic energy. That means I can come back and say that this is also 0. That means what we end up with is kinetic energy of the system at point 1 is your total energy, because there is no potential energy, because there's, the object is on the ground. It doesn't have a height. So it only has a motion energy. So the total energy is just based on the motion energy. But at point 2, it doesn't have a motion energy because it stops. No kinetic energy. But it obviously changed the height. That means now it has a potential energy at point 2. And that's what we basically going to be verifying. Is the height that's going to reach, which is like, let's call this h, let's say the point 2, is indeed the representation of the potential energy that is exactly equal to the kinetic energy. That means our goal will be this. So find the relationship between kinetic energy of the object at point 1 and compare it to the potential energy of object at point 2. And idea here is, for a very specific speed that it has at point 1, you're going to get a very specific height at point 2. That means if you have a specific speed, you can calculate then the kinetic energy. And based on that kinetic energy, then you can say that kinetic energy at point 1 will be exactly equal to the potential energy at point 2, which means that 1/2 mass times speed 1 square, which is kinetic energy at point 1, going to be equal to then m times g times h2, which is the potential energy at point 2. So you can see, right, if you kind of looking at this, what we have here is that, see, this is the speed at point 1, and this is height at point 2. And then the idea here is that speed at point 1 square is proportional to the height at point 2. So that's why if you have a different speed, you're going to have a different height. But always you're going to have such that if you calculate this quantity for point 1, which is 1/2 times mass times speed at point 1 square, you're going to get exactly same quantity on the right side. So then we can explore this to find, if I calculate the specific speed, will I reach the height that I'm predicting or not? So that's kind of like, let's say, the experiment going to be verifying. Because if you calculate the speed and calculate the kinetic energy, then from that the potential energy, and then experimentally or theoretically calculate the height, then you should be able to verify that by doing an experiment and testing your prediction. That means, for example, what we have is that 1/2 mv1 square equals mgh2. So technically that's your equation. See, one of the important things here is that mass actually cancels out. So it doesn't even matter what type of mass we have. It could be a block, it could be a box, it could be an elephant, as long as it's on a frictionless surface. And then from here, we can see that H2 is equals to 1/2 times V1 square over G. So technically, this is our equation, which is going to be already plugged in for you in the table in the lab. But the idea here is that if you know the speed at point 1, then you can calculate the height at point 2. Then every time you have a new speed, you can calculate new height. Then when you go and repeat the experiment, you can then test that. You can see how high it goes and then verify if whatever you calculated as a prediction can be verified with the experiment. Okay, so that's basically our experiment. All right, so let's go to the lab, the Pivot Interactive Lab, and see what's happening there. Okay, so here's our experiment, conservation of energy. So for this one, you can see, right, in this activity, we will make prediction of how this system will act based on conservation of energy. Then we'll test our prediction and see if it is correct. All right, so here's you can see, right, what we have in this video, it shows a superconducting pack and magnetic track. The pack is cooled at the negative 196 degrees Celsius in a liquid nitrogen bath. Then the pack is placed above the track, held in position by a wood spacer through the process called quantum locking. And it basically creates a frictionless surface. So through the process called quantum locking, the pack remains the same height above the track. So basically, it's kind of levitate about that. Watch the short video below to familiarize yourself with the apparatus. So this video just gonna show you what's happening, like let's say the setup itself. All right, so you can see it's actually very cool because you are using the concept, basically the concept of thermodynamics and quantum physics to, set up that particular experiment. In any case, so once you watch the video, go ahead and submit your answer to a couple of questions here, and pay attention that you have multiple submissions, some of them even overkill. But the idea here is to learn, understand. If you think about it, give it a minute, think about it, and then submit your answer. If you got it right, that means you're on the right track. If you got it wrong, think about it, and obviously, if it's just two options, right? So choose the one obviously that is the correct one, and try to understand why. So these are sort of like a preliminary questions to get you going. So in terms of what is the equation for potential energy, and hopefully you can already recognize that. What is the equation for the kinetic energy? Hopefully you can recognize that, and those type of things. All right, so then one of the things we have here is also, if you're given the pack as 100 grams, you need to then learn how to convert that into kilogram, remembering that 1,000 gram is what we define to be 1 kilogram. So use this conversion factor to calculate mass of the pack if it's exactly 100 grams. What will be the mass in kilograms, basically? Okay. Now, then you're going to like your answers. Then we go to the predicting the height. So in this part, we're going to be looking at the experiment to predict height. And remember, so our goal here is to predict height will be in terms of, remember, so we have 1/2 mv1 square equals mgh1. Okay, that means since mass is the same for both sides, we can cancel out. And the idea here is that if I know the speed, then I can predict the height, because looking at this equation, then what I can say that h1 is equals to v1 square over 2g. That means in a way, this is the equation for the predicting the height. Okay, so again, it's going to be already plugged into the table, but the idea here is this particular video allows you to see only the launch part. There you go. That means, as I mentioned, right, so this can be considered as position 1, and then it's going to go to some height, which is position 2. We don't know where it is, right? Maybe here, maybe here. So we don't know where it is, but the idea here is that we can predict using the equation and the calculation and the measurements that we do. Now, our goal here is to find how fast it's moving here. What is V1? Well, we can do that by remembering that speed is defined as distance over time. That means, for example, if we start from here and it moves this distance d, and if we can measure the time it takes for the pack to go that distance, then we can find the speed at which it's moving at exactly through 0.1, because as soon as it goes up the slope, it starts slowing down. Okay, that means, again, if we kind of go back and look at the experiment, you will see that basically it starts from somewhere over here, then it's given a kick, right? So then you can see, right, it kind of moves, let's say, this distance. So that means you can stop right here. Okay, you can, like, let's say, stop right there. Okay. So let's see what we can do. So playing the video, going back when it's right here, let's say. You can see, right? Then take out the timer, reset the timer, take out the ruler, put it right there and measure the distance. So you can see, right? So this is roughly, I would say about 13.5 centimeters, right? So let's say it's 13.5 centimeters. And the idea here is if I play the video, then it's going to be synced. That means what you want to do here is look at, okay, so starting from when time is 0, how long did it take for it to go and reach then basically that position 1, after which is going to start going up a slope. That means here I have 0.0667. Okay, that means those are my data point. That means this is basically for that distance. I have this particular time. So then using that, V equals D over T, we can calculate that. But everything will be done technically inside your data table, because if we kind of scroll down here, you will see that there's a table where you can see, right, this was trial 1. So we can say that for the trial 1, the distance that we chose was, let's see, what was it? It was, okay, so the distance that we chose was roughly, let's say roughly 13 centimeters. So we can say that this is 13 centimeters. See, then this is the distance in meters, which you can do by taking the distance in centimeters and divide it by 100. Then it can convert to distance in meters. Then we plug in the time, and you can see, right, 0.0667. So let's say 0.0667. Then it's going to give you not only velocity, it's already going to calculate for you, but it's also going to give you kinetic energy. Okay, so that means you can right away then get the kinetic energy. Then your next step will be do the same experiment for trials 2, 3, 4, 5. Basically choose, you can see, right, I have 5, any random 5 try, let's say it doesn't have to be 1, 2, 3, 4, 5. So for example, let's say you don't have to do 1 because I'm showing you the experiment here. You can do then 2, 5, 6, 7, any combination of 5 different trials. So for example, if I go to number 3, so then I have something different, right? So it's going to be moving a little bit differently. So that means you do the exactly same process though here for this particular experiment. So for example, you go and you can see, right? So basically it's going to be, it's going to be launched. So you take it, put it here, and then maybe measure how long it will take to cover 15 centimeters, because 15 centimeters right when it's going to start going up. So reset and play and go like this. That means, go back and say, all right, so I want to know how long does it take to go right there, which is 0.0833. That means right now you're going to say for this one, I chose 15 centimeters and it was going at 0.0833. And then it's going to give you speed and kinetic energy. All right, so you're going to do that for another 3 experiments. So then you're going to answer some of the questions here. Then the idea here is, because we are assuming that it's a conservation of energy, well, potential energy is going to be same as kinetic energy. That means you're going to come back here and you're going to say, okay, my potential energy for my trial 1 was 0.190 because my kinetic energy was 0.90. Because see, what we have here is when the puck goes from the bottom of the incline to the top of the incline, the only force acting is the gravity, which is a conservative force. So potential energy will be exactly same when it goes up and stops. That means you can say that, see, for example, if I do 0.190, enter, so then here I'm going to have a height. Then you can then use this equation, right, to calculate technically the height, which will be, so if you take this, you can say that my potential energy then divided by, well, what you have the mass and gravitational acceleration. So you open parentheses, then you say, well, mass is, whatever you calculate, right? 100 gram converted to kilograms. So let's say then it will be whatever mass you have. So let's say 0.1, then times 9.8. So if you do this, submit. Oh, I forgot to close the parentheses. Submit, and then you have your height. That means it's going to go 0.94 meters or 19 centimeters until it stops. Then you do the same thing for the other one. Let's say 0.162. So 0.162, enter, and it gives you then the height. Okay, so then you're going to do that for all of them until eventually you do for all the trials that you chose, 5 trials. Then you're going to like your answer. Then we're going to go to predictions. That means now what you have here is, for example, remember, this was my trial 1, where I say that height is going to be 19 or 0.19 or 19 centimeters. Okay. So then when I take this vertical, a ruler and put it here, see 19 going to be something like this. That means it's going to go up to somewhere right here until it stops. So it's somewhere over there. It means this is going to be my 0.2. So because that's basically where I have 19 centimeters, right? Roughly speaking. And then we're going to be then doing the experiment to predict. Okay. All right. So actually, I have to scroll up a little bit, but we have the meter stick right next to that, so we should be fine. So that means if I play the video, we can see, we can predict, right? Oh, it goes a little bit higher than that, and it comes back. I guess, if I take this and move it like this, so technically I would have predicted that to be somewhere right here. I think it was 19 something, so almost 20, so something right there. So let me double check again. All right, so it's a little bit of difference, but again, we're close enough. And remember, I didn't really do very accurate measurement because I was kind of giving you an example. So you should be a little more careful, making sure that you have an exact measurements of distance, exact measurements of time, and take your time to make all those measurements and do the predictions. But that's pretty much what you have to do. So that means for everything that you chose, right? So then you're going to calculate height. So if you see that this is 19.6, or let's say if this is 20 centimeters roughly, then this will be 0.2 meters. So then you're going to go up and compare. So here I have 0.19, here I have 0.2. So is it correct? Is it wrong? Well, you talk about how close your predictions are to the actual result. Remember, there's always room for a little of errors, right? So which is a lab. That's how things work in the experimental lab. So don't worry if there's a slightly little bit difference, as long as you don't predict 10 centimeters and you get 25 centimeters, right? So if the difference is like only a few centimeters, that's actually very acceptable. That's what even probably what predicted by the experimental errors. All right, guys. So hopefully you're okay with this experiment. It's a relatively nice and straightforward experiment by basically finding the conservation of energy, finding the height from the prediction, and using the fact that kinetic energy and potential energy are exactly the same for those 2 points at the bottom, at the top of that incline. All right.